Morning, sir. Good morning, sir. Are you able to hear us?
Yeah, now I'm able to hear.
Okay,
I'm
okay.
audible now.
Okay, yes, sir. Yes, sir. You're audible, sir.
Yeah, good morning. Very good morning. Thanks
Good
for
morning, sir. Good
inviting
morning.
me for this presentation.
Yeah. Thank you, sir. Okay, sir. We'll start at 10:30. Still
Yeah,
have time.
sure.
Yes,
Sure,
yes.
we'll do that. Meanwhile, I will just try to share my screen and I will check.
Sure, sir. Sure, sir. Ashok will be there. He will be
Yeah,
assisting you.
yeah. Thank you.
Okay, sir.
Ashok, are you able to see my screen? Yeah. Okay, I will just move this slide. Are you able to see the video is playing there, right? Okay. Yeah. Okay. I will just.
Okay. So, good morning, all the participants. I welcome you all to the fourth day of this Northeast Center for Technology Application and Reach Nectar sponsored 1-week entrepreneurship development program on flexible 3D printing operation and prototype development. We are really pleased to have amongst us Dr. A.K. Lakshminarayan, sir, from the Department of Mechanical Engineering, SSN College of Engineering, Chennai. So before starting off the session, I would just like to brief you about our speaker for today. Dr. A.K. Lakshminarayan sir has been recently featured in Stanford's list of top 2% scientists in the world 2019 and 2021. Sir has done his BE in mechanical engineering in 2003, ME in manufacturing in 2006, and PhD in 2012 from Annamalai University. Sir has a Google citation of over 2,315, and sir has been actively working in the field of materials joining, advanced metal forming processes, additive manufacturing. Sir is currently supervising 6 PhD scholars and completed 2. And sir has been actively involved in professional activities, which includes section editor in friction welding, Welding Technology Review Journal, Society of Polish Mechanical Engineers and Technicians. Sir has also been a recognized reviewer for over 20 referred international journals published by Elsevier, Springer, and Taylor Francis. He is also the life member of Indian Welding Society, and Sir has also worked in several collaborative research projects with Professor Philippia A.S. Reid from University of Southampton, UK, on applying of DIC to dissimilar welds. Then he has also been actively involved with national laboratories such as IGCAR, DRDO, and NMRL. Sir has, to his credit, 2 books edited on materials and manufacturing by Transtech and Springer. Sir has also received a Vishwanathan Iyer Prize for the best PhD thesis in manufacturing from Annamalai University during the year 2013. And Sir is also the recipient of DST SERC research grant under Young Scientist Scheme for the development of friction stir welding tools to weld stainless steel. So with this very brief bio sketch, we would like to invite our speaker for today, Dr. A.K. Lakshminarayan sir from SN College of Engineering, Chennai, to kindly start off the session. Sir, please.
Yeah, thank you, Professor, for the nice introduction. And I will start my presentation on fusion and solid state metal additive manufacturing. So we also called as 3D printing techniques. So we will see a few fusion-based additive manufacturing techniques, as well as also solid state processes, like mostly friction-based solid state metal additive manufacturing techniques. So am I audible now? Is clear? Voice is clear, right?
Yes, sir.
Yeah. If there is any if the videos are
I will
not
inform,
playing,
sir.
please let me know so that I will play it again, right? Yeah.
Sure, sir. Sure, sir.
Yeah. One second. So no, no. I hope the previous speakers talked more about 3D printing, right? So just to refresh this, so basically, we have three different types of manufacturing here. Formative manufacturing, separative, and additive, right? Additive manufacturing is what we call it as 3D printing, right? So formative means forming, right? You will just take some material in some form. Okay, you just yeah, some noise is there, right? Okay. So you have a bulk form of material, just you deform into particular shape using some kind of die and punch arrangement. Okay, basically bulk deformation process. Okay, that you can do. Separative, you will take a bulk material like this. You will be using a tool and just remove the excess material, whatever you don't want to have. Suppose these areas, the material is being removed using a tool, right? Usually, this is a milling cutter, which is used to, in this case, it is a milling cutter, which is used to remove the excess material, right? Like that, whatever the profile you want, you just remove the excess material, right? This involves a lot of scrap, right? There are a lot of waste, which will accumulate. For example, if you take magnesium alloys, suppose I want to fabricate a component, using a magnesium alloy. So if you have a lot of scrap material, there is a problem. Especially magnesium alloys will catch fire when it is in powder form. So retaining the scrap itself is a big issue. In addition to the waste production, right? So whereas in case of additive manufacturing, as you heard a lot about 3D printing last few days, so we will be constructing or fabricating a product layer by layer by just programming the path of the tool, right? Just you will melt the feedstock. Okay, the feedstock may be powder or wire. So you will just melt layer by layer. You will just try to construct the material, right? In this case, no, you will though it is called near net manufacturing, still you will have some waste, but no, the wastage is so much reduced, right? That is the advantage of 3D printing or additive manufacturing. Okay, one more example what I have here is, suppose if you want to make a screw. So what we usually do, we just take a stock and try to fix it in a lathe and try to use a single point cutting tool, try to make this thread, right? Just you try to make this thread, then you whatever material you have here, just you remove it, just finally you will get this product, right? So until the desired product you get, you just try to remove the excess material. But in case of additive manufacturing, start with nothing. So just you have a substrate, okay, over which you can just place some powder here, just melt using a laser. Okay, that is called laser powder fusion bed. I hope you heard something on that, right? So, or you can also use some kind of wire. You take some wire, the wire is melted and it is be deposited as a layer. Okay, like that, you gradually you add layer by layer, so that you will end up with this product. Okay, similarly, until desired product you will get, you will just try to build layer by layer. That is why adding layer by layer, that is why it is called additive manufacturing, right? So most of the additive manufacturing, research, if you take research volume of research done by the researcher, most of the additive manufacturing papers, right, available there, majority, right, they are all non-metallic materials, right? Mostly non-metallic materials are very common. No, in recent years, people they started is gaining importance. In other words, it's gaining importance for metallic materials, right? If you take metallic materials, so you have four categories here. One is powder bed fusion, the other one is directed energy deposition, binder jetting, sheet lamination. Okay, so in this case, you can use the powder fusion bed is very simple. So you have a cavity like this, right? Just you imagine a cavity like this. You just put some powder, use the laser just to melt a layer, right? This layer is melted. Again, spread some more powder on the other layer. Just again melt it like that. You will construct. There is powder fed fusion. Okay. Here the source may be laser or EB, electron beam also you can use. So you can have a beam of photons, or you can have electrons also, electron beam also. You can use it for melting, right? So here the feedstock here is the metal powder. Okay, here is the metal powder. In case of directed energy deposition, again you can have, here you have three sources, right? One is you can have electron beam for this, or you can also have laser. Here one more thing is wire arc. You can also use arc welding process. No, very soon we'll see. You can use arc welding processes to melt the wire, and you can deposit. Okay, here you can use metal powder. The feedstock is metal powder or metallic wire, right? So directed energy deposition you can use. Here in case of binder jetting, you will be using metallic powder. In case of sheet lamination, you will take a sheet, try to cut by laser or something else, and place one over other just to glue it, right? This is by one way you can use laminated object manufacturing. The same technique, which is not very popular among researchers, is there is a technique called friction stir additive manufacturing. Take a layer, try to keep one over other, try to weld it, okay, by friction stir welding. You will see that in the later stage. So today I will concentrate more on wire arc additive manufacturing, that is called WARM, and which is not given in this category, but still I feel I prefer to put this in this category, that is called friction stir additive manufacturing. Okay, friction stir additive manufacturing. But even within this, we have several classification. We will see that one by one, right? So if you consider, suppose if you take wire or powder, which will be better? People will immediately ask, which will be better? That several criteria we have to compare. Just a comparison is given here. The feedstock is here, it is wire, and here it is a powder. Suppose if you take titanium, the you see here it is 120, right? 120 here per kg. How much it is cost? Here powder, it is 280, because production of titanium Al64V, right? Ta6Al4V, right? The production cost is so high. That is why you see just it is almost two times to 3 times it is higher, right? So similarly, just in codon also, the powder cost is so high when you compare the wire. Not only the cost, and also the recycling, right? The powder, when you produce the powder, right, you need to know the energy spent during the powder production is so high. So the deposition of wire will be somewhat better, right? So if you see, there are several techniques. If you take if you want to compare these processes, you have to consider two factors. One is deposition rate. Okay, deposition rate, how much gram you are depositing per hour, right? This is in the y-axis. And minimum feature size. Okay, what is the feature size? You can fabricate, right? If you consider this area, right, this quadrant, if you see up to this, you can use powder bed. Okay, powder bed, you can use laser source or electron beam. Say, since you are using powder and you are using source, right, a very concentrated source, the feature, right, the size also it is somewhat less. The deposition rate also it is less when you compare other process. But the surface finish will be very good. Okay, that is the advantage in case of powder fusion bed. In case of laser LMD also, somewhat it is higher. Arc based, you can still go for a higher deposition rate. The feature also bigger size. Okay, and there are other welding techniques, right, in which you can deposit more, right? You can large scale manufacturing. Okay, large deposition. Okay, that is possible in case of arc welding, and the feature size is also very big. But when you go, if you increase the feature size here, and suppose if this is if you go this way as in the diagonal, your surface features, right? The surface finish, it is somewhat poor, and you need additional machining. Okay, you need additional machining. That is one of the drawback of high deposition rate. Okay. Wire arc manufacturing, I will concentrate more on wire arc additive manufacturing initially, then I will move on to friction based additive manufacturing. If you take wire arc additive manufacturing, it comes under directed energy deposition process. Okay. In this case, we will be using a metallic wire, okay, which will be supplied at a particular rate, okay, a constant rate that we can vary, and we can play with that also. Where now the metallic wire will be completely melted, okay, and it will be deposited in the previous layer. That means, so initially this is the substrate. So initial layer will be deposited using a wire, okay, with a heat source, right, with the arc, right. Maybe your wire, based on the welding process, your wire will be melted, the arc will be created between your wire and the substrate, or sometimes between your electrode, non-consumable electrode, and your substrate, and the wire will be fed externally. Okay, that we will see. Okay, so wire arc additive manufacturing means you will be using a wire. Okay, you need a arc source, right? You need a heat so arc by means of any of the welding processes. So this wire will be melted and it will be deposited. First layer will be deposited, then again it will be lifted. Your torch will be lifted up. So again another layer will be deposited. Like that, you can deposit, right? So across the globe, people are in many countries, they started working on these processes, right? Especially wire arc additive manufacturing processes. Few are listed here based on the report by Wu et al. 2018. You have in India, though it is mentioned only in IITs. Many groups are working in NITs and national labs also. They are working. We also started some work in intermetallics, and we are also working. My specialization is on friction stir welding, so we are also working on friction stir additive manufacturing. So wire arc additive manufacturing, you have many different names, right, which is being called welding based deposition, welding based rapid prototyping, 3D welding, 3D micro welding. This is also very popular. One of the concepts, earlier concepts, proposed by one of the university from Japan, right? I hope it is from Osaka. So near net manufacturing, hybrid layer, okay, shape deposition manufacturing. Different names are there, right? We will see what could be. And later part of the initially we will try to understand what are the variants of wire arc additive manufacturing. At the later stage, we will be seeing solid state additive manufacturing techniques like rotary friction welding based, linear friction welding, friction surfacing, friction deposition, and friction stir additive. This is very much popular now with respect to the product. Okay, additive friction says no, it is a patented process by Aeroprobe. Now there is a company called Meld. They are also working on that. We'll see that. So one second. So this is a laser, right? The wire is fed here, okay, and with the laser they are able to melt it, right? This is how. This is initially a multi-track single layer. Okay, once single layer is over, if you want to build, continuously, you can build it. So your wire is fed. This comes under directed energy deposition. We will be using laser to melt. The heat source here is laser. Okay. Of course, you need to decide what is the overlap you should have, because between tracks, to avoid porosity, usually, the overlaps is provided. So any contour shapes or any shape you want, just you just prepare a CAD model, just you create the path, then you can just move a touch laser source, whatever you want, right? Whatever shape you want, right? But the problem here, if you use the laser or electron beam, the energy whatever we are using will be very, very high when compared to the arc power. Okay, that is very important. That is why people want to know they want to use warm process. Warm is wire arc additive manufacturing. That is one of the reason. One is the energy consumption, which you consider when you compare with the laser and electron beam. It is 1/10th of laser and 1/30th of electron beam generator. Okay, that is one of the biggest advantage of warm when you consider economy. Okay, and the other aspect, large deposition, large metal deposition is possible. The deposition rate is very high in case of warm. Okay, that is also another advantage. And one more thing is, if you consider material aspect, aluminum, copper, magnesium, they because of their reflectivity, if you want to use laser, the energy, the laser source should be absorbed in order to generate the heat. But unfortunately, aluminum, copper, magnesium, they are all highly reflective materials. So that is not a good choice for these materials, especially laser. And if you consider laser beam, electron beam, you all know you need a vacuum space because air molecules will interact with the electron beam and it will disturb the beam path. Okay, so there also it is very difficult to operate, especially it restricts the size of the product. Okay, so arc selection, if you say if you go, there are several arc processes are there, right? Starting from gas metal arc welding. We will see some of the pictures of that, the schematic of that. I will try to explain it because there may be students here. So requirements, you need relatively, why you want to go for arc related process, you need relatively high deposition rate and heat input, low heat input to the substrate, and stable process. Okay, these are the requirements. Based on this, we can select any one of these. Okay, gas metal arc welding, gas junction arc welding, plasma arc welding. We will see one by one processes, right? So if you see the arc welding source, uh, these are the four processes very commonly used. That is, one is gas junction arc welding. The schematic what you are able to see here is a sorry, this is a GMW process. Maybe in the next slide I will show GTW process. Okay, so in case of gas metal arc welding, so you have a wire which is fed continuously, and the arc will be initiated between your wire and your workpiece. Okay, this will be continued, and this arc, the wire will be melted and it will be deposited. So your wire is fed coaxially within the torch. Okay, this is a torch, right? That is, you need not want to feed wire from the outside. Okay, external feeding is not required because your arc is your arc will be initiated between your wire and your substrate. Okay, so but unfortunately, uh, the arc stability is very poor, and a lot of spatter you can see in this video. You can see a lot of liquid metal which are ejected out, right? That is called spatter. So then the generation of spatter is huge, and you can also see a lot of fumes. Okay, these fumes which will affect the welder or the operator who is doing this operation. So that is also another problem. Okay, but the advantage is, since the torch and wire, they are coaxial, path generation and the programming, it will be easier. Okay, that is the advantage of GMW process, gas metal arc welding or gas or metal inert gas welding. Okay, MIG, it is also called as MIG. So here the heat will be generated by striking an arc between your the wire and your substrate. Okay, that is the advantage of GMW process. Okay, yeah, sorry, I'll just go back. Yeah, this is one second. I'll just play this video, right? Yeah, this is GTW process where you will be using a tungsten electrode, which is a non-consumable electrode. Okay. In previous case, in case of GMW process, we used a consumable wire. The process uses a consumable wire. The arc will be stuck between your consumable wire and the substrate. In this case, you will be using a tungsten electrode, which is a non-consumable electrode. The arc will be stuck between your non-consumable electrode and the substrate. Here the wire we are feeding the wire externally. That is the difference between the previous one and this process. I'll just play this video again. See your arc, it is coming. There is a external wire which is fed from the front side, right? It is a front feeding. The advantage of this system is since you are feeding the wire from the external source, you can control the heat input and filler addition in a better way when you compare SMW process, GMW process. And also the wire feed direction and positions you can you can modify it. In some cases this is beneficial, in some cases it will create problem. But what advantage we have here is you can use back feeding, side feeding and front feeding. What is that? That means here it is front feeding, right? They are feeding from the front. It is moving in this direction, so they are feeding it from the here. This is also possible, right? From the back side you can feed, or suppose if this is your torch, right? This is your torch. This is your tungsten electrode. Okay, you can also feed it from the sideways, right? You can also feed it from the sideways. So this is front side, right? We are seeing from the front. Actually, this is a side view. Okay, this is a side view. The feeding here is from the front side. This is one more video. You can see here the wire is feeding from here. Now you see this is the substrate. No, this is the first layer already melted. And you can see the second layer. You can see the liquid metal here, right? So this is your GTW arc. You can see the wire feeder here. The wire is fed here. It is being melted here. I hope you are able to see. Here it is being melted. This is in the longitudinal direction. Okay, this is in the longitudinal direction. This is the first layer actually. Whatever the layer, yeah. And this is the actual setup. So this is your work table. See, you can either move the torch or you can also move the table. Okay, it depends on the machine you have. Okay, either you can use robot. When you use robot, most of the time the torch will move. If you use a CNC table, so usually the work table will move, right? You can have these processes, right? They don't provide self shielding, right? We have to provide the shielding gas in order to avoid oxidation. Okay, this is the arc. It will move in this direction. This is from the wire feeder. The wire will be fed into the liquid, the arc, right? Exactly in the arc column. So it will be melted. It will be deposited, right? You have to use cooling also from the back side so that the undesirable microstructure can be avoided. Okay. So you can also use plasma. Okay, this is plasma arc welding. Okay, that also you can use. The difference is in case of gas tungsten arc welding, your nozzle, right? Your nozzle is this, nozzle cover is this. Okay, I will just draw it like this, right? This is your tungsten electrode, which means, right? This tungsten electrode is projecting outside, so your arc will diverge like this. Whereas in case of your plasma, so your arc is constricted, right? Because your tungsten tip is inside this nozzle, right? Inside this nozzle, thereby this arc is constricted. No, not like this, right? It is going, this diverges. There is no restriction here for the arc. Okay, but here it is. You have a restriction. Okay, so this process is also you can use these processes, right? Laser and plasma arc welding, they are all high energy density processes. So still you can use this for additive manufacturing. Okay. So you may use GMW, you may use GTAW, gas junction arc welding, or plasma arc welding. Okay. All these three are very popular. There is one more variation which we call it as CMT, cold metal transfer. We'll see the mechanism of that also. So if you consider the whole system, right? So you need, these are the components of the warm system. Okay. So you have you need to have a welding machine initially. Okay, you need to have a welding machine. So you need to have a controller which will give feedback to the computer. The sensor, right? Whatever the sensor, we can measure temperature, or sometimes even vibratory signals also, acoustic emission signals also you can record. So those signals will be sent to the computer as a feedback. Based on that, you can modify the parameter using this controller, which will modify the parameters in the welding machine, so that whatever the desired condition you want to have, you can modify it. So that the welding machine is connected to the robot system, so that whatever the program, whatever you have written here, so based on that, this robot will move, right? This axis, the robot will move and it will deposit. Okay. So this is a GTW machine. As you see, there is an external wire feeder here. There may be tungsten, non-consumable tungsten electrode, right? So if you don't want, see, even in GMFW also, you can feed one wire here, you can feed another wire here. Okay, suppose if you want to modify the chemistry of this material, so you can have both is possible, right? Suppose if you want to add some alloying element, you can feed that as a separate wire also. Okay, not necessarily the external wire feeder should be used in GTW only. Okay, you can also use it in GMW process where you want to add some alloying element to the system, right? So this is the robotic setup. This is one way you can do warm process, and this is a system usually used for friction stir welding, solid state process. Just they modified it. It's a CNC system. Okay. So all these axes, the table will move, right? This will move, the tool head will move this way, whereas the X and Y axis, the table will move. Just based on the CNC programming, you just, instead of tool, FSW tool, you fix the torch here and you can deposit. So these two possibilities are there to manufacture components by wire arc additive manufacturing. You can also use hybrid processes like GMW and GTAW. Both you can use. Okay, to improve efficiency, right? Because there is another process which we call it as cold metal transfer welding. In this case, it is a modification of GMW process developed by Fronius company. So in this case, there will be short circuiting. Once the wire touches this, right, there will be short circuiting. This droplet will come. Once it spreads, like the wire will be retracted. Okay, so I'll just clear it and play this video so that you will try to understand that. Yeah, second, I will just play this.
Sir, can you share the links also, because right now our class is also going on, so daily we are not able to attend these sessions.
Hello.
Sure. We'll share the video, recording video, right?
Okay, sir. Thank you, sir.
Yes, sir. You can continue, sir.
Yeah.
Thank you, sir.
Yeah. See, here you have a, once the material it will have contact here, there will be droplet formation because of short circuiting. So then the wire is retracted so that the it will lead to the droplet which will be transferred to the substrate. Okay, I'll just play this video here, the right side one. You can see how it works actually. So the droplet is transferred. Now the wire is getting retracted. Yeah, just watch this. I will just let you know. Yeah, sorry. Yeah, the advantage of this is, yeah, I will just stop this. Yeah. The advantage of this, right? The deposition, no, it is high quality deposition. Almost no zero spatter. When when I have seen that video right on GMW, lot of spatter is there, right? In this case, no, it's a droplet transfer is there. Droplet short circuiting transfer is there. So absolutely no, the spatter is almost negligible, right? Or is so much reduced. So the average deposition, right, it is somewhat 2 to 3 kilograms per hour. Okay, this is cold metal transfer. Okay, this is another application of cold metal transfer. How actually a complicate or complex geometry you can still fabricate, right? See here how it is. This is one of the variation of CMT. It's called pulsed CMT. You just this transferred, right? It's a droplet transfer. You can able to see that. This is one of the variation by which you can even create complex product, right? Arc additive manufacturing, whether it is a near enough shape manufacturing, but it depends on deposition rate, accuracy, and surface finish. Okay, always as I mentioned in the initial slides, there is a compromise. If you want to produce large parts with a high deposition rate, the dimensional inaccuracies, right? Always know the dimensional control is somewhat difficult. That's what I mentioned in the beginning. Similarly, small parts, you will get very good accuracy, but it is at the expense of productivity. The time requirement, which will be very high in case of small parts. If you want to get good accuracy, the productivity will be less. Okay, that is the drawback. But that depends on the application for to which you want to apply these components, right? Especially if you want to produce components which will be used for fatigue loading conditions, you need very good surface finish. As we all know, the fatigue failure always initiate from the surface. So your surface finish will be very good if you want to have material with very good fatigue properties, right? So if you consider the approach how to build the bead, people have used several techniques. These I have taken it from the TWA website, and this data. You can fabricate beads this way. See, how will you do that? Say, suppose if I want to produce a component like this, suppose this one, right? So what I will do, I will layer. I will deposit a layer, right? I will move the torch this way, right? So I need to create the path for this, right? Path planning is very important step in additive manufacturing. So either I can start from here. I will just go one pass, just move my again. I will come here, start here. Again, I will come here, like raster scanning, right? So I will just do that. This is layer 1. Okay. Then I will start from here. This is layer 2, right? Say this is layer 1, right? Layer 2, layer 3, layer 4, like that it is going, right? So this way again, this like this it will go. Okay, I will start with here and like that I will go, right? This is layer 1 and right. This way I can do that. Or also I can just reverse it, right? So this, in this case, I can go this way, same direction or reverse direction also I can go. Okay, same direction I can deposit, reverse direction also I can deposit. Okay, here starting point is reversed. Okay, layer 1 starting point is here, ending is here. Here starting point, ending is here. Okay, or otherwise I can go in this. This is longitudinal direction. This is transverse direction. I can also So when I take a when I take a job like this, either I can scan this way, or I can also take shorter path also, right? I will do this way also. Why we want to do this? Because no, the thermal profile, right? The heat generation during each pass, between passes, right? So suppose if you deposit one layer, if you want to go for next layer, the interpass temperature is very important, and overlay area. Okay, all those will affect the final property of your material, and most of the time, it will affect your residual stress. It will affect the temperature, right? The temperature is very important. Controlling the peak temperature is very, very important. That is why people want to try different path, right? The path, if you during the path planning itself, so various path we have to try, and we have to finalize a particular path based on the peak temperature, right, or temperature profile, which will subsequently influence all microstructure, residual stress, and distortion. Okay, that is very important. That is why the path strategy is very important. So far, in the literature, right, just to have some idea what are the materials already tried by various researchers using different warm system. VAM aluminum alloys, if you take almost starting from these are non-heat treatable alloys, 5000 series, and also these are heat treatable. Again, these are 4000, 5000, they are all non-heat treatable. Again, these heat treatable, right? Both heat treatable, non-heat treatable people have tried using GTW process, TIG welding process, or cold metal transfer. GMW also people have tried, right? I told you some of the problems with that, but still people tried that. Okay. Titanium, if you say plasma arc welding, GTW is very common for titanium, because the control of spatter and interaction with the external atmosphere, right? It is controlled, well controlled in this process, GTW and plasma arc welding, right? So steel, most of the steels, right, they tried with the GMW, GTW, plasma. Okay, mostly all these processes being used by Inconel 625, super alloys, CMT, PAW. Okay, just you can go through that. I can share the slides. Okay, and as I mentioned, you can use robot CNC for just to deposit the material. As I mentioned, GTW, it will be using a non-consumable electrode, separate wire feed system you require. Orientation you have to control, because so when you have the wire, so what orientation you have to, whether with the horizontal it is 15 degree, whether it is 30 degree, that you have to optimize. Okay, so that your wire will feed into the arc column, and your melting will be proper. Okay, in order to have proper melting, it should be your wire should be fed at a particular orientation, so that your deposition rate also, this will affect your deposition rate also. So melting also it will affect, deposition rate also it will affect. Okay, so again plasma, same thing. Almost since it is a high energy density process, almost the deposition rate is somewhat higher, 2 to 4 kg per hour. GMW, it is very high, because the production rate, deposition rate will be 3 to 4 kilogram per hour, because you will be using a consumable electrode. That's why the production is very high. You can also use tandem 2 GMW torch powers and torches. The deposition rate, if you see, much higher. Okay, 9.5 kilogram per hour. Okay, so you can use, as I one of the picture I showed, you can use both combination of GMW and GTW, right, which provides GTW here bypass current it provides, and material utilization, how it is being melted, it will be improved. Okay, CMT, as I mentioned, it is a low heat input process, because this wire, right, this wire is retracted after the droplet, right, once the droplet forms, this will be retracted. So further heating is not there for this liquid metal. Okay, so this is a low heat input process as you compare to the GMW process. So good arc stability is there, almost zero spatter. Okay, the deposition rate is around 2 to 3 kilogram per hour. But in few cases like titanium and aluminum, there may be a problem of arc wandering. So the arc, no, it is not able to be get stable. It depends on material again, but most of the material CMT is good for warm process, right? See, what are the defects which will be there in case of warm? The first problem is residual stress. Okay, the stresses which are built within the material, that is because the one layer, if you deposit a layer, suppose if this is a layer deposited initially, again I will just deposit another layer. If you deposit it already, some layer of this will be melted, right? So again this will be melted, and it will be at a particular temperature. It is not at room temperature now. It will be at a particular, because it is undergoing cooling. There will be interpass temperature. Again another layer like that. If you know, there will be accumulation of heat. Okay, there will be accumulation of heat. So that causes sometimes the stresses built within this material, which will be exceeding the yield point. Okay, exceeding the yield point of the material. Okay, if that is the case, if a residual stress built within the material exceeds a yield point, the material will undergo deformation. Okay, so your material will be deformed. Okay, suppose I want to have a shape of this. Okay, but unfortunately, because of the residual stress, I will end up with this kind of deformation, deformed structure. Okay, so to avoid that, usually what they will do, rolling treatment. I have a video for you. After a pass, what they will do, they will do a rolling, which will induce compressive residual stress. See, there is the residual stress. You have two nature of residual stress. I hope many of you know, tensile and compressive. Tensile is not good for us, because suppose tensile always it will tend to suppose if you have a crack, I will just explain this with the help of this diagram. If you have a crack, if you pull this, right, we pull this with a load 100 megapascal, if you just pull it, suppose if the crack tip will have some residual stress which is tensile in nature, say for example this is 20 megapascal. So now the load applied is, even though it is 100, the actual stress acting at the tip, right, it is 120 megapascal. So that means it will tend to open this crack. Okay. So always in a structure, tensile residual stress, it's not desirable. Compressive is desirable, because suppose the same case, if you take, to understand it, I'm just trying to put this example. So if it is a compressive residual stress, okay, 20 megapascal, same 20. Now actually the tip 80 megapascal. Okay, though you are applying 100, the tip it is only, because this is minus, right? So there will be crack closure. Okay, instead of crack growth, crack blunting will happen. Okay, so always in a structural member, tensile residual stress is not good. So for that, what they will do, if they want to reduce the stress, rolling treatment will be done. Sometimes ultrasonic vibration is also will be used to avoid this residual stress. And one of the other problem is porosity. Sometimes your material will have surface contamination. Say for example, wire, we are using a wire which may have hydrogen atoms, because it may be wet. If you are not properly dry it, or it may have some contamination which will cause pores during solidification. Okay, so shielding gas production you have to give, and you have to use clean wire, right? So that is also other thing by which you can reduce the porosity. What people suggested, there is a novel method called hot wire arc additive manufacturing, that will reduce energy input as well as porosity, because whatever the hydrogen atoms are there, that will be just when you use hot wire it will go, right? That's it. That's one of the reason you can use porosity, you can reduce. Crack and delamination is very one of the problematic thing, especially heat input is increased. When you increase the heat input, I told you, sometimes accumulation of heat will lead to crack. Okay, crack also form when you mix two different metals, okay, which will have two different physical properties. Say suppose I melt, I provide aluminum from one side and steel from another side. So when I melt both, right, there will be, these two are not compatible system, especially when it is liquid state. So naturally the crack will form. Okay, there are some mechanisms, don't worry right now. Similarly, magnesium suffer from hard cracks. Even aluminium also suffer from hard cracks. No, what I mentioned here is bimetallic materials, right? That means suppose I want to deposit a stainless steel substrate, I want to deposit a copper on that, right? I just want to deposit a copper. The problem is the melting point is 1083 here. This is 1459 around that approximately. So this is one problem. The melting point is there is a huge difference in the melting point. The other problem is the thermal conductivity. This is, we all know this is a good conductor of heat. This is a very poor conductor of heat. So naturally there is a thermal expansion. Everything is different. So usually there will be crack formation as well as delamination. This will not adhere to this. If the melting is not proper, it will not adhere to the stainless steel. So these are some of the common defects, and we cannot generalize this. It depends on material. Okay, that is why this curve, this graph is very important. You have deformation is one of the problem, which will be caused by the residual stress. Porosity is another problem. You can see porosity is there. Surface finish is very important. That depends on how much deposition you are doing. Crack, you can see crack here. Oxidation is high temperature. Oxidation is one problem. Okay, some material will go under oxidation. Delamination between layers, there will not be proper bonding. Okay, the number is given here. Maximum is 5 and minimum is 1. And you can see titanium, aluminium, steel, different metal here. Porosity is biggest problem in case of aluminum. See the color here. Okay, porosity is the biggest issue in aluminium. When you compare these four material, or you have bimetal here. If you bimetal, if you see the residual stress is huge. Since you can correlate it easily, right? Here residual stress is high. Deformation is also high for the same material, bimetal, right? Because you have more residual stress whenever it crosses yield point, the deformation is high, right? So like this, just you can get the data for some material. You can plot these kind of graphs to understand what is the real effect on the product, right? So these defects, they are not acceptable when you, especially when you apply these component in a critical application of like fatigue kind of loading. Okay, repetitive loading. Okay. So to review this, what we have here is a warm hardware system. Basically, it depends on 4 welding processes: gas tungsten arc welding, plasma, gas metal. Cold metal is nothing but it's just a modification of GMW process. In case of GTW and PMW, you need separate wire feeding system, that you have to remember. Okay. In case of GMW process, the higher deposition rate is possible. CMT, arc, in case of GMW, the arc stability and spatter problem is there. CMT, low heat input, especially since you are attracting the wire during the droplet transfer, the stability of the arc is very, very good. The executing unit, if you see, you can use robot, here robot or CNC. CNC, as per the literature, CNC is always expensive but higher accuracy. Okay? Robot economical, and you can easily it's flexible to adapt it. Okay, this is with respect to the warm hardware system. Okay, hardware system. Physical process, if you take parameters, these are the parameters: current, voltage. You all know when you do welding, right? Welding speed, wire feeding speed, what is the substrate temperature, interpass temperature, what is the arc length. Okay, arc length is very important, right? How much wire, if suppose if this is your torch, what is the length here, right? So distance between your beads, okay, distance between your beads, maybe suppose if it is a single layer, overlap, okay, one layer if you deposit, next layer you have to deposit just adjacent to that, how much overlap you need to provide, that is what distance between beads. This is in horizontal direction. Suppose I want to go in vertical direction, suppose I build one layer like this, when I want to deposit next layer, how much distance I want to go so that there will be some overlap right here in vertical direction also. So that is also very important factor you have to consider. The second factor, this is technology that you can control. Heat accumulation factor is another thing that we have to, I told you, some cooling you have to give. Gas might be through gas or even some cooling setup, also it's possible, okay. Then arc and droplet behavior is entirely different, right? In case of GMW it is continuous, in case of CMT it is droplet, okay. You can also monitor this process by optical detection method, acoustic emission. We are also started some work in this. Recently we bought one of the, we are going to buy this, we got a fund. We are going to work on that acoustic emission for wire arc additive manufacturing. You can also, we have thermography. We have a very good system for thermography also. So we are working on these two areas. No, you can say, no, you can electrical detection also possible. How much your voltage is varying with between passes, how your current signals, those you can study and you can just correlate with the properties, okay. So properties, if you try to understand the property, first you need to solve this issue: residual stress and deformation, porosity, crack and delamination. Okay, so, lot of application people know already. I will show some of the videos in the forthcoming slides. Wings, spare and landing gear, propeller, large, no, lot of application already people have tried that. Different companies already tried that. In future, you can use modeling aspect is still a lot of modeling aspect. Still, you have a lot of scope, especially application of machine learning in WAM and the even finite element analysis is required. Still, you have a lot of opportunity to do that. Hybrid technology in the sense you need to use deposit. Just when you do deposit, in order to have better finish, you have to do some machining. I will show one of the videos for that also. You can use additive subtractive technology. Just deposit a layer, do some machining, again deposit the layer, do some machining, finally just finish the component by some machining. Okay, that is hybrid additive subtractive technology. In addition to that, you can use rolling just to improve the property or reduce the residual stress. Okay, that also I have a video for you. I'll just show you. Okay. Again, if you take quality performance, process selection, that is what we discussed so far in the last thing, last slide. Feedback optimization, whether you will be using standard wire or wire mixing, you want to use two different wires, mix it, or you need to prepare wire, even you can use flux core wire with some alloying elements. Okay, post process heat treatment is one of the area we need to work on. Okay, all other properties, strength and ductility usually we evaluate, but fatigue damage, corrosion property, still the data is missing, right? Data is not so openly available, right? So quality improvement is here. Okay, this we already discussed. I just want to skip this. This is one of this note slide where you can see what various defects with respect to the material fabricated by warm process, and here the material is here. What are the processes used here, and whether you will, based on this actually the plot was drawn, what I showed you to you. So this is the process where you have a arc source which is moving, okay, followed by a roller, right? There will be some kind of loading. Now it is moving. Actually, now roller will come. You just wait. This is a deposit. Okay, I hope it is on third or fourth layer. now, sorry, second layer. Now the roller comes here. Okay. Still, this is in hot condition. Yeah, this is a hybrid process, right? You need somewhat additional setup, which is used to still the initially your arc is depositing. This is it is depositing a material. Again, it is followed by a rolling. Okay, that is one of the hybrid technique you can use to improve the properties of the fabricated product. Okay. This steps continues, right? Layer by layer. For each layer, we have to repeat this. Yeah. So some of the products, this is the some of the products by Canfield University and Norsk Titanium Company. Also, they have fabricated this, wing spare, landing gear. You see, just imagine, suppose if you have to prepare this by a machining process, what you have to do? Take a big structure, big material, right? Big, large material like this. Then you have to do machining here, right? Then you have to do machining here. You have to do machining here. Okay. So that is the problem, right? Lot of material saving you can do when you consider machining, casting and machining. If you do, you have to do lot of machining. That is not required here. Okay, that is the advantage. Almost now many literature says no. For this case, around 470 kg, they saved it. Okay, so when you go to conventional machining and this, okay, this is some of the components by BAE Systems, high strength wing model. This is hollow structure and mild steel truncated cone. Okay, that is also possible. Okay, so I'll just play this video. It's not playing. Wait a minute. So this is some of the components. You just program the path, and you can see this is GMW. You can see a lot of spatter which is coming out. So now they are doing machining. They will just use a end mill cutter just to do machining. I told you, this is a hybrid technology, right? Just do between process also you can do, or you can also do at the end also. You just finish it. That's it. Just use a end mill cutter. Finally, you will get this finished product. Same thing if you want to fabricate using conventional methods, either you have to go for, see how much, how good is this component is. So this is some of the components which fabricated through a warm process, just to have some idea. Yeah. So, right. So the limitation, whatever we witness, right? Fusion-based metal additive manufacturing. Basically, it uses powder bed fusion or directed energy deposition principles. But all these method, right? They use fusion, right? They use to melt the material, which will end up with molten pools. And these techniques usually suffers from other problems, like though you are able to produce component, there are some you need to always go for post-weld heat treatment. Okay, because there will be solidification related issues specific for a specific material. So that is one of the drawback. That is why people wanted to try solid state technique also, right? Solid state technique, basically, as I mentioned in the one of the slide at the beginning of this lecture, you can use friction welding. Friction welding itself, you can use rotary friction welding or linear friction welding. Also, you can use friction stir. There is a process friction surfacing. We'll just, for the sake of students to understand, just I will show some of the videos to understand the principle of the process. This is rotary friction welding. So here, if you see, this rod is rotating, right? This is rotating. This is moving in this direction, but it is not rotating, right? So because of the frictional contact between these two rods, right, we are applying force from this right. Okay. Yeah, this will again. I just yeah, he is inserting the rod, one of the rod here. Okay, another rod, the other side of the chuck. It is similar to a lathe, right? No. Yeah, this is moving. Initially, it will have some contact. There will be frictional heat generation. Yeah, initially there will be frictional heat generation. So then I'm applying some more press. There is a flash which is coming out, right? I hope you all studied in manufacturing. I don't want to spend more time on that. This is linear friction welding. In that case, no, your rod is rotating, right? In this case, it is oscillating. This is stationary, and this is oscillating in this direction. This is stationary. We will be applying force from this side. This side. Yeah, I'll just play it again. Yeah, okay. This is linear friction welding, right? The third one is friction surfacing. Okay, just this is a substrate. Second. So this is your substrate. This is a consumable rod. Okay, this we call it as mechatrode. Okay, we are applying force from the top. So because of that, there will be frictional heat generation. The material will go to this condition, right? The temperature is around, above it's 1200, right? So the material will be transferred to the surface. You can see the deposit is there. Okay. This is the consumable tool which is rotating at a higher speed, right? It will be around 3000 RPM. Okay. So I'm also applying force from the top. Okay. So the material at the interface will deform. The only thing is the substrate should be harder than the tool, right? This is called mechatrode. The consumable rod is called mechatrode, right? See here, initially it is being plunged. You will have friction at the interface that creates a lot of heat. Okay. So once this is undergo this will go to the plastic stage. So your tool will be moved in this direction, right? There will be deposit. The third process, the last process is friction stir welding. Here you have two sheets here, two material, two plates. Okay, you have a tool. See, you have a tool of this. No, you have two portions here. Okay, one is called shoulder. Other one is pin, right? So initially, I will just plunge inside. The pin will go inside. Okay, suppose I will just draw it here. I have a plate. Okay, two plates are there. Okay, initially my pin is there. Okay, my tool shoulder is there. This is larger diameter is called shoulder. Okay, this one is pin. So what I will do, I will just try to plunge it inside this joint line. So once it goes here, how would it look like? It will look like this, right? The pin will go here. The shoulder will touch at the top surface. The shoulder will touch the top surface, right? This is the actually these are the two plates, right? So since it is rotating, you have pressure from the top. The material from one side will go to this side, and this side will come to this side. Okay, that will be mixed properly. Okay, so whatever the material beneath this shoulder, so there will be bonding. You will get a bonding like this. So this is butt configuration. I can even join lap configuration. In fact, friction stir additive manufacturing uses lap configuration, right? So I can use tool here, just plunge it, stir it, so that I will get a bond here. Okay, I will try to do that. So show you that. You just see this video. Initially, the pin is going inside. just it is going into the joint line. It is going inside now. That it is going into the budding line. The shoulder will get contact with the top surface of the sheet. Two plates, right? Here you have two plates. The shoulder will, once the shoulder gets contact, the more heat will be generated because the contact area is now no, it's larger when you compare the pin area, right? So now the material is getting deformed. Whatever the material beneath the shoulder, so it will undergo deformation, plastic deformation. Please try to understand here there is no melting involved. Okay, all these process, whatever I mentioned, it is a solid state process. There will not be any melting, right? But this is only I am talking about welding now. Using by the use of these process, we will do additive manufacturing also. Okay, that is what we will share in the next slides, right? This is a copper plate. This is a copper plate. That is why the temperature is going to this red hot condition. Okay, these two are copper plates. So which is very difficult to weld by conventional welding process, copper, because of the conductivity and other issues. So distortion issues, very clean weld you can get. Okay, in this case. Okay, right. So using this process, right, especially people have tried many aspects, right? So the frictions additive manufacturing. See here, they will take a substrate. They will just keep a plate there, strip there, and they will try to weld it. Stringers, right? Stringers assembly, right? So, see, this is your main sheet. Take a main sheet or main plate. Place another plate here. Strip, right? Or yes, stringer, right? Try to weld it here. Try to weld it here. Like this again, keep another plate, try to weld. Like that you can just deposit one over others, stack the sheets, try to weld it. Stack the sheets, that you can do by friction-stirred additive manufacturing. Linear friction welding, no, just blade to disc, that we call it as blisk. This is called blisk for gas turbine applications. You can attach these discs to the blade, okay? So, yeah.
Sir, after the welding, we have to do machining.
Here you need not want to have any machining. Here in this case, no, it's a direct deposition. Might be a small cleaning you may require.
Because sir, you said that we are putting one layer, then after we are welding at certain place, a desired place, and then after we are putting another layer. So the layer is different size.
Yeah,
Sir?
in between, in between you may in between you may require to slightly finish it. I will show you a video. You will understand it. I have a video for you for that. Yeah.
Okay.
Yeah. So you can use linear friction welding, and also you can use friction surfacing also. As I said, no, consumable rod you can use, and you can just deposit it. One layer you just try to deposit, another layer again and again you can deposit like this. Okay, that is also possible. Rotary friction also people use. I will share some of the slides because of time limitation. See, this is where this is the first step. Friction welding by use of, there is a process called friction deposition by friction welding. Just you have a substrate, you have a consumable rod, you just move this. Because of the friction there will be some deposition. Once you stop the rotation, right, you just stop the rotation and move this tool away, right, you will have a single layer. Then you just try to do some machining as you rightly asked it. The machining is not so and you will not remove too much of material. You will only slightly remove. You will remove only small amount of material, right? Just layer, right, to have uniform layer thickness. So you can build this kind of layers. Okay. So this is restricted to rotary components. Okay. This problem, one of the disadvantage of this method is only by this is one of the work by Dilip et al. In 2011 from IIT Madras. Just you do one layer, two layer, like that they are depositing it. Finally they will do machining. They will take actually the side also, it is not coming very good. They will take this as a final product. The advantage is this of this one, no, even if you take cast alloy, you take a cast material, okay, which will have no very big grains. So you see only 4 grains, only 3 grains. If you do this, if you take a microstructure from here, you can see small refined grains because of dynamic recrystallization. Okay, plastic assisted new crystals, when it forms due to plastic recrystallization, plastic deformation, you will get very fine grains. Okay, that will have very good properties. Okay, that is the advantage. Okay, people may ask why, if you have a rod, why we want to deposit like this. Especially one way to answer for those questions, if you have a cast alloy which will have a very big grains, so that will be, the grains will be refined in this and properties will be improved. Okay, this is one of the method, friction deposition, thereby layer by layer you can just this is another work, the same group, but the material is different. Okay, there is another method, friction surfacing. The video which I have showed, right? One layer you try to deposit by friction layer, try to do some machining, then you deposit other layer, like that you can do that. Okay, so this is the actual steps involved. This is your substrate, this is your consumable rod. Just apply some force, it is rotating at a particular speed. Your material at the interface with respect to the tool, it is deforming. So once it is plastically deformed, it will be moved and a layer is deposited. This is the first layer. Okay, just take this out. You have to remove here also. No, you have to remove this part. Again, deposit it. Like that, you can do multiple layer. Okay, like this. No, you can even you can change this rod in between. You can do deposit functionally graded material also. That we call it as FGM. Functionally graded material is also possible. Okay, this is one of the work, same group. You see, you have a base plate. This is first layer, second layer, third layer, and fourth layer in a first pass. Okay, sorry, this is first layer. This is pass number 1, pass number 2, pass number 5 passes, right? Similarly, just on the top of that, they deposit like that. You can see here how good is that. So you can do that slightly, do some machining, you'll get this one, right? I will just skip this because this is not related to this one. I'll just go to friction additive manufacturing. Okay, here no, this is butt joints. As I told you, if you want to join 2 pieces like this configuration also you can try, but various configuration also possible. There is one of the earlier work was from Professor Prasad Rao from again IIT Madras, 2016. Stack 2 sheets, try to join it. Okay, by lap welding. Okay, again the pin will enter into the joint line at the interface. It will go into the interface and will try to join at the seam weld. If you see the cross section, actually the bonding will be so like that. The bonding will be like this. Okay, just erase this line. So the bonding will be like this. So once this layer is, once you deposit, this is first plate, this is your second plate. So keep another plate. Okay, keep another plate. Try to weld it here. Similarly, you can build layer by layer. This is only 2 layer they have done. You can also go for multiplayer. In 2017, we have tried. This is base is actually magnesium. Top we try to attach a thin sheet. This is for corrosion. Similarly, you can stack layers. Many layers, if you want, you can stack layer. Even you can change the composition. By metal, I don't want to go in detail about this. The paper is available there, and even you can get it from a Google Scholar. Okay, you can see the bend test. Even if you bend test, that is very good without any cracks. Very clean bonding is there. This is what I told, right? One layer is, this is first layer, second, third, fourth. Okay, just bond it here, bond it here, bond it here. Like that you can go. So if you want to know multiple passes this way also you can bond. Okay, all this joint we have fabricated magnesium alloy, 8 layers, and each layer will have 8 passes. Okay, we have material which we have yet to publish it. Okay, as he asked, right, initial plate preparation sizing you have to do. Just stack one over other, do some FSW run, desired height is achieved. So again, this is the final build. If you decide the height is sufficient, you stop there. Otherwise, just flatten it. They can do it. Okay. Some of the work which is published by Yu King, no, in 2018, they tried 7075. Okay, 7075. They stacked like this, right? They joined. They evaluated the properties like they have very good. This video will show you some of the if you have any doubts on that. Actually, this is now they are doing FSW. Okay. Any contour shapes, no? If you have a proper fixture and the tool, no, then you will. Now, actually, a milling cutter comes into contact and just remove the surface. You know, some flashes is there. It will remove the material, right? They will keep another plate. Again, try to do FSW. Yeah, that's it. So the cross section is look like this actually. So this is a single pass and different layers. Okay, this is 1, 2, and 3. This is the first pass maybe. Okay, suppose if you want to go for this, no, here also you can go. Okay. See, this is nine layer build, right? This is C. See here. Okay, you have different passes are there, right? Some overlap will be there, transition zones that we have to take care. Okay, you have to control the heat input so that there will not be any problem like a heat affected zone or people have tried with magnesium alloy also this technique. I will just try to help you to understand the process. I will skip those. These are same thing. Okay, I want to show some other aspects also because of the time limitation. I am skipping some of the slides. So some applications, so especially functionally graded structure. So in this case, sometimes you may need a sandwich structure. This is alloy 1 and this is alloy. In between, you can have various alloy, or you can have in between same alloy and different layers, or alternating gradient structure. Alloy 1 is this, alloy 2, alloy 1, alloy, like that it will go. Fully gradient. Okay, you will start with a particular alloy. You will change each layer. You will be presenting different alloying element or different alloy. You will end up with entirely different alloy on other side. Why we want to have? No, in many applications, no, you may use one of the sides. Suppose if this is the parting line, this sides, this material will be subjected to high temperature. Okay, but this side you may subject the material to only corrosion. This is immersed. Okay, the temperature is low. Might be this like this condition. No, you need to have functionally graded materials or even gradient structure, because for high temperature application you need a property. For a corrosion resistance you need another property. For one example I can quote is stainless steel to chromoly steels wells, right? So you need different properties at two different ends. Okay, this is one way. There is one more technique, same thing. You just make a groove. You just prepare a groove, put some powders, use the tool to just stir the material, okay, so that the powder is distributed at the bottom like this. This is the step. Step 1 is grooving. Step 2 just to stir it. Then again you have a groove there. Just create a groove. Again put the powder, stir it. Like that is all. Like that also you can gradient. You can functionally graded material. You can still able to do that. And if you consider solid state, you have other systems also. Okay, this is what we there is one more technique which we are going to see. Very interesting technique. But in foreign countries, Western countries, they already adapted this in for manufacturing. This process was invented by Aeroprobe, and now popularly it is being used by Meld company also. So here there is a tool which will have a hollow portion here. So what we can do, we'll just send the powder, or the feedstock may be powder, or sometimes it's a solid wire also. Okay, we will be sending this wire through this hole, but this will be rotating similar to FSW process, and the powder will be deposited. Okay, this is called additive friction stir. Okay, this process called additive friction stir deposition, very popular. Okay, the rod, it may be rod or powder they form. You see here the grains, you can see very fine grains. You are able to see very fine grains. In case of, you can also use ultrasonic vibration. Say this is a roller. You are sending, you are just sending a feed foil. You are sending a foil. So when it goes inside, because of this vibration, so see ultrasonic principle is, so suppose this is your one of the surface. If you have another surface like this, so you have peaks and valleys, right? When you vibrate it, what will happen? These peaks will get collapsed. So finally, what you will get metal to metal contact, and you will get bond. Okay. So at the interface, always you will get refined grains. That is what you are able to see here. In interface, fine grains, but away from that, that means this is a localized deformation. In case of ultrasonic assisted additive manufacturing, the deformation is localized. But it is here, it's bulk form. That is why the grain size is uniform and it is homogeneous. In case of additive friction stir, right? There are several other techniques. I don't want to go in detail about that. This technique is very useful. Okay, to print 3D components. Okay, the deposition rate is also very good. Material loss is also very less. So this is a substrate. As I told you, this is a hollow tool through which I am feeding the material. You can just control the path. You can even deposit this kind of circular cylinders, 6-inch OD. This is of aluminium 6061 medium strength alloy. As I mentioned it was patented by this Aero probe. Actually, one of my friend, actually Dr. Kumar Kandasamy, he was with IAC Bangalore. Then he worked in Aero probe. He patented that actually. Okay, actually it was patented by Indian. Okay, so but US patent because he worked there actually in Aero probe. Okay, so continuously you can deposit this kind of. This is much better when you consider friction stir additive manufacturing. You can see hollow, just feed this wire, try to deposit. I will show some of the videos so that your understanding will be better. Some of the benefits what we have, this is a non-beam process. We don't have any laser beam or electron beam or even plasma beam. Hence no melting is involved. This is a solid state. Energy associated with very less. Cost is also very less. You can use cast alloy rod. You don't want wire which is fabricated through rod structure with a rod structure like wire drawing. Those secondary thing is not at all required. Cast alloy directly you can use it, or consolidated powder also you can use it. This process is a scalable process. You can build large scale parts, high build rate, and even if you have some crack, you can still able to repair it using the process. That is one of the very good advantage over other process. If you consider the properties, as I told, the material will undergo dynamic recrystallization, which will cause refined grains, and also equiaxed grains. If you see grains morphology, if you take a columnar grains, if it is there, properties will be entirely different. If you have equiaxed and fine grain, equiaxed in the sense the grain from the center, if you reach the boundary, almost the distance is almost it's equal, right? That's why it's equiaxed grains always will have very good property, and the property will be isotropic because it is not localized deformation, it is a bulk deformation. So the property will be isotropic. No solidification, that means the porosity is reduced, the residual stress is very less. Okay, hard cracking tendency is not there because solid state processing. So elemental segregation is also not there. So that is also another almost different exotic materials you can try with this process. Okay, so this is how actually it works. You have a hollow cylinder, inside you have a screw which is rotating at a different speed. So whatever the particles, it will be forced through here to the thing. So it will pass through this path. There is a gap. So this is also rotating. Because of that, there will be frictional heat generation, and it will go to plastic state, and it will be deposited. Okay. So you can one layer, 2 layer, 3, like that it will go. There you can have different layers to deposit it. Okay. From the powders, machined chips also you can deposit. That is one of the recycling is one of the very important concept. Especially as I told at the beginning, magnesium chips. If you want to recycle it, still you can be able to recycle it by this method. But here it is a non-heater 5083 building industries, they are using this. You can see the grain structure, very refined grains and equiaxed structure you are able to get. This is the process. Just you can watch this. How might be you need some machining on the side, on the sides, but you can it's a very fast process, solid state process, very important. It is mentioned. You see how clean this. You are not able to see any radiation. There is no arc. Fumes are not there. So that is one of the advantage of this process. This is environment friendly process. Okay, that is the only thing. But we need no machines. We in India there is no machines available now right now, to my knowledge. So might be in future, we will also work towards this process. So this is various materials you see even in circular form or in cylindrical deposition. Suppose if you have a cylindrical section, if you want to improve the surface properties, still you can do that in the right top corner, right? You can do that. In the bottom left one, stringers. Okay, especially these stringers, if you cast and do machining, lot of waste around in this only from 200 kg to 18 kg they mentioned it, right? These stringers, if you fabricate within 18 kg, will finish the structure. But when you do machining, casting and machining, always you need to use large amount of material. That is also one of the drawback. And as I mentioned it, the grain structure. Okay, grain structure is very, very important. Even you can use some kind of what do you call bimetallic tubes also you can fabricate, or the dimetallic cylinders. Okay, so inside first in this layer is this is a different material. Suppose this is maybe aluminum. This layer is magnesium. You can also reverse it. Even both sides you can have aluminum, in between magnesium, thin layer of aluminum on both sides, magnesium on other outer sides. So that will lead to weight reduction. Okay, weight reduction, and also the corrosion resistance of the magnesium alloy is it is protected. Okay, so by this you can these are some of the problems still people want to explore. If you see the build rates, you just imagine the build rate of aluminum. It is around 1020 centimeter cube per hour. Whereas you just check the other process, how much fast you can fabricate the component. Okay. So this process still we need to work on. Plenty of work we need to be done. This company Meld, they are fabricating this kind of a porous structure also you can fabricate. Continuously, if you build, you can build foams also. Okay, that is also one of the other application. There is one more material called oxatic material where negative Poisson's ratio. That also is possible by this method. People have demonstrated that. See, this is your base structure, rolled plate. Okay, see the grain structure. This is the grain. Okay, see the grain here. Very big grains. Aspect ratio. You check this, but you see here the grains. Okay, after the in this process, you will have very good. That is, even if you do this, take a bulk material, machine it. This microstructure is there as such, but in this case, the properties also improved. That is very important to understand. Okay, you can use build a component like this, or if you want to repair work, you can do that. Coating, you can still possible, as I mentioned, aluminum, magnesium combination, copper, stainless steel combination, or you can do that. even dissimilar. Sometimes in between you need compatible method, because this side, suppose if it is P91, that side is 316. In between you can put inconal transition joints. Still, no, by this method it is very useful. Okay, so we have to try that also. Some of the examples for you to understand. I'll just skip this because of the time limitation. I'll just quickly rush through these slides. You see here how they are building the component now. Even repair work, most of the time, sometimes this kind of rib fracture, sometimes these ribs, it will get fractured. Okay, here. That can be done. The ribs, even if it is fractured, you can just repair it. Okay, just by depositing using this technique. Okay, people have demonstrated it. This location of worn surface, try to solve this by just depositing material there. Okay, this is what I told you. If you want to improve the surface finish, this is also you can do. Okay. This is another area where this is a nickel aluminum bronze used in ship propellers. This material is subjected to erosion, corrosion, right? Erosive environment, corrosive environment actually. Why? Because this material, sea under, sea water, it is a salt solution, as well as sand particle will have contact, because when it rotates, sand particle will have interaction with this surface and try to damage the passive film, and corrosive environment will now have interaction, and it will lead to a lot of corrosion, right? So erosion, corrosion, cavitation erosion, those are the problems for this material. So suppose this is very big structure. Okay, we cannot, suppose if we have a crack here, we cannot throw as such. So we have to do repair work. That is possible. You see here, damaged areas, you can just do repair work by this method. Okay, that is also some of the other advantage. You can see some of the other products: 60 pressure vessel dome and rocket nozzle. Okay, this is the Army rail. These are some of the application proposed. You can see a video in YouTube. I just taken it from that. You just go through that. Okay. I'll just, okay. Yeah. To summarize solid state, you can use friction stir, friction surfacing by consumable rod, friction deposit by just rotating tools, or you can attach the blade to the disc. This is a disc actually. This is actually disc. You can attach blade by. This is popular process actually, especially in conal for gas turbine applications. Friction stir will additive friction stir is very popular nowadays. A lot of potential for that. As a solid state technique, especially soft materials like aluminum, copper, and even dissimilar materials. Okay. Yeah, that's it from my side. Thank you very much. I would like to have some questions or some interaction so that I can share my. Thank you very much. I thank the organizers for inviting me to share my experience, as well as some of the data available in the literature on the metal additive manufacturing. Thank you very much.
Thank you so much, Lakshminarayan sir. It was really a very good session. We would definitely like to take few queries, if any. Any participants having any queries may ask. So one thing I would like to ask.
Yeah, please.
So there are a lot of heat involved in these processes, right?
Yes.
So actually, how do we overcome all those residual stresses due to continuous heating and cooling?
Yeah, that is why I told you, sir, you can use some kind of cooling arrangement. One thing is gas cooling at the trailing gases you have to use. That will solve two purposes. One is it will avoid oxidation. The other one is it will just cool the the metal which is deposited already. That is one way you can do that. Or one more video I have shown, the rolling you have to know the control, the heat input you can control by, initially you have to control by process parameters only. Okay. Most of the literature, they mentioned, though they have overlap areas, but it is not affected as in the case of welding. Okay, especially in case of welding, you may see heat affected zones. But whatever the literature available, most of the, we also done some work. We are not able to see, there is a overlap region, but it is there is no heat affected zone, because one by one layer, it is deposited, because one layer is cooled, then we are sub. It is not like a butt joint where simultaneously both the metal will be melted. There the problem of heat affected zone is there, but in this case, one layer is cooled, then we are going for another layer. So most of the time the problem is not there. But the thing is, you have to control the parameters so that your heat input is reduced. That is one aspect. That depends on which material you are working on. Suppose you are working on a heat sensitive material, definitely you have to select a process where heat input is so much less, like CMT, cold metal transfer. That is the first step. The second step is you can use some sort of cooling arrangement and shielding gases to control the thing. The other thing is, in order to reduce it, you have to use hybrid techniques like residual stress. You can reduce by rolling. That video I already shown. Another thing is, try to do some machining after each pass. Hybrid, additive subtractive technology. That is, now people are using that technology. Just try to remove distortion each step, because it will not accumulate. So that is the next step you can do. Right?
Okay,
Is it
okay,
okay?
thank you, sir. And yeah, so one more thing, and regarding the path that that needs to be followed during the deposition. So there is no such predefined path, right?
Predefined path, no, you can use similar to polymers, how you are depositing. You can create CAD models. You can use slicing, and you can just generate path also. Path planning is very important actually, but this is still at the infant stage, and research is going on. Except few components they have fabricated. Path planning is necessary, essential here. Path planning is essential, and that is why I have shown that one of the slide I have shown various path also to control the thermal profile. The previous question, that is also one of the reason. So path planning will whatever the path you follow, that will affect your thermal profile. So you have to know the strategy. You have to create a strategy where your thermal profile should be proper, or the peak temperature must be within the limit, so that you will get desired properties. So path planning is essential. Like whatever you do for polymers or other non-metallic, here also you can do the same thing. You can create a CAD model. You can use both, right? Robotic system and CNC. But here also you can use some software to control the path planning.
Okay, right, sir. Thank you, sir. And any more questions from the participants? Mohan sir, any question?
Sir, can you hear me, sir?
Yes, sir.
Yes,
Yes, sir. You are audible.
please, please.
Sir, I have one question. So we have seen sometimes that we are getting some void in the 3D printing, sir.
Some, please.
Void, sir. Void, sir.
Yeah, whites.
Yes, sir. Yes, sir. So how to avoid this, sir? Because this voids are making weaker to this product, sir.
Yeah, that's what I mentioned it. The porosity, cracks, in addition to the residual stress and deformation, this another problem is the porosity and cracks, right? So that depends on material. That also I have shown a chart. Not all material will suffer from porosity or voids. In the chart, if you see there, in the video again, if you play, aluminum, it suffers because of they are prone for porosity formation, especially when you melt and solidify it. So it can be controlled by many ways. One way is you have to use hot wire. Okay, that means you have to heat the material wire also, so that the hydrogen atoms will not go into the liquid metal, so that you can avoid porosity or small voids. That is one way. The other way is when you deposit layer by layer, what the gap, right? The overlap is very much important. Overlap, if you suppose provide some gap there between two passes, that will a lot of gases will be entrapped there. That will also create voids. So when you overlap is also a very important factor. That is why I mentioned in the question, right? For the questions, right? Path planning is very important. Path planning also lead to voids. Okay, depends on the material. That is why solid state process, right? Especially aluminium, copper, those are additive frictions. You will not end up with porosity or defects. No, because they are all solid state process. The material will not go to its melting point. There is no problem of porosity. Okay, there will not be any problem of porosity. So you have to select a process depending upon the material, right? So fusion welding, definitely still you are able to control the porosity by just optimizing the parameter and how your void is fed into the arc. All those things will decide. Okay, what is the interpass temperature? Everything will decide. Ultimately, heat input to supplied and thermal profile. By controlling this, you can still control the porosity. People have if you see the cross section published in the literature, you can still they avoided porosity by controlling the parameters.
Thank you, sir.
Yeah, sir. Welcome, sir. It's welcome.
Yeah, thank you, sir.
Yeah.
I guess any more questions? I guess there are no more questions from the participants. So I would like to request Ashok, PhD scholar from the Department of Mechanical Engineering, to kindly conclude the session. Ashok, please.
Thank you, sir. Thank you, Dr. Yagi, sir. It's one of the best lecture in the schedule, in your busy schedule. I personally tell few things about the Dr. Yagi, sir, because he published more than 110 research article and also research review articles of around more than 150. And personally, he is one of the mentor me to guide as a friend, as a brother, help more on research work. And he also research and he also motivate many persons like my friend Alvin of IIT Madras. He joined under the guidance. He is a main person to motivate each and everything. He also motivate many scholars personally and financially also. So I request all the participants, you have any doubt, any queries, meet or mail them personally. We always open our mind to help our project. And also I thank Dr. Akil sir once again for the wonderful lecture. Thank you, sir.
Thank you, Ashok, for your kind words, and thank you very much. I will be available. My mobile number is with Ashok, and my email ID is there in my slides. If you see the video at the end, you can just contact me for any help. I will try to do. We'll also try to collaborate for research also. Thank you very much for the opportunity again for the organizers. Thank you very much.
You,
yeah.
Thank you, sir. Thank you. Thank you.
I am leaving, right? Thank you.
Okay.
Thank you, sir.
Yeah.
So with this, we come to the end of the first session of the fourth day of this EDP program. I request all the participants to kindly join us back in the second half, that is from 2:30. The session will be handled by Mr. Sofikur Rahman from Tool Room and Training Center, Guwahati. Thank you all. Do join us back in the second half. Thank you.